Hello coders, welcome to my video. So in this video, we'll be starting off with a very interesting topic, that is the memory layout of the C program. Okay. So what happens when we compile a .c program and we get a binary, and when we run that binary, for example, we got a.out, that is a default binary name in C, and when we do uh, slash a.out, the bash will, you know, instruct the kernel to execute that binary and make it a process. Okay. So for that, the operating system or the kernel allocate memory to store the program instruction and the data and applies a predefinite memory layout. Okay. So what is this layout? Okay, so if you see here, you have one C program or a .c file, and it got compiled using GCC, and we got a binary executable of the format .a.out, right? And when we run it on a bash, it goes or load into the RAM and it becomes a process. So the flow from a binary package to a process, there is a memory layout of that binary that is defined by the kernel. So there are two types of memory layout. So first one is a static process memory layout, and second is a dynamic process memory layout. So what is the difference between the two? In a static memory layout, this is created by the compiler and fixed in every exe. So every exe have the same memory layout when it is in the form of a binary. Okay. So it is not yet been created as a process. Okay. So when this .exe got into a process or converted into a process by the OS, there is a dynamic memory layout. So the memory is typically divided into several sections. So we'll study these all sections first. That is a part of our memory layout. So whether static or dynamic. Okay. So we'll see what all segments are there in a static layout and what all there in a dynamic layout. Okay. So if we start from the lower address size of this memory layout, we have segment. Okay. Then we have data segment, and then we have these BSS segments. And there is a heap and stack as well. And there are other environment variables and the kernel variables that is stored on the higher addresses. Okay. So if we talk about the segment, data segment, and BSS segment, these all comes in a static memory layout. Okay. And the memory layout of stack and heaps are there in a dynamic memory layout. Okay. So these, what do you mean by that is, if the text segment, data segment, and BSS segment is defined at the compile time and it is present in the binary. But this stack and heap that comes into vicinity when that executable become a process. Okay, so we'll see this how it happens. So first of all, we have the text segment. So what is this text segment? This is, first of all, it's a read-only section. This is the code of your C program which you create. For example, we have int main something. So all the code that is stored in this segment. So there is some space partition. Okay, that is a virtual memory space that is allotted to this section when a binary executable is created. Okay, so if we change the text segment and compile it, this space will change. Okay, we'll see how these things can be altered. Okay, so second is a initialize global and statics. Okay, so for example, we have this data segment and we have a static variable. defined globally or locally. So that static variables comes into this segment. So whatever, if we define static int a, so that comes into this segment, it is automatically been zero. Okay. So if we are not initializing any of our variable, it directly comes to the BSS segment. For example, I have a global variable int x. Okay. And that variable should come in BSS segment. Okay. So these are the three segments. Let's explain these all in practical form. So I'll take a local variable int global var1. Okay. And I take a global var2 as well. So this is uninitialized global variables. So if I compile and check this with the size here, so you will see here you have the text segment, you have the data segment, and the BSS segment here. So all these are the static memory layouts, and here we have the file name. And if you see here, we have 1480 of text data in your binary, and you have data segment 544, and 16 is the BSS segment. Okay, so this is after we take uninitialized variables here. So if I take two more, so I take 2yy and I will use 3 and 4 here. And now if I see, I need to compile it again and then I use this. So if you see here from your last data, so this remains the same, but this BSS segments from 16 to 24. So this is 8 bytes. So we have two integers that we added as a part of global variable, and that comes in this BSS segment due to that variables are not initialized. So what I will do, I'll initialize that value. Okay. And what I initialize, I will initialize variable 3 to 10 and variable 4 to 12. Okay. And I need to compile it again, check the size. So if you see here, your BSS segment drops to 8 bytes because we have two integers. So from the uninitialized section, 8 of the bytes are been minus, and here if you see 8 bytes are been added. Okay, because that two variables we initialize it. Okay, so this way we get to know that the variables from the data segment and BSS segment goes into which area. So similarly, if we have increased the text segment, it will increase that text area. So from here, we analyze our binary in a statically form. Okay. So our next part is the dynamic memory layout, that is of heap and the stack segment. So for that, for our stack segment, we can have integer local var. Okay. And for the heap segment, what I can do is I can take a char pointer and use malloc to get the memory, for example 10 bytes, because this heap segment is taken by the variable that is allocated through malloc arc alloc or realloc. So all these dynamic memory allocation APIs allocate the memory in the heap segment, and all the local variables goes into the stack. Okay, so then I'll print the addresses here. So printf, I have the address of local variable or local underscore var is equal to percentage p for the address. So I'll take address of local var this way. And if I need that address of this memory, I can get it from this memory pointer. Okay, so then I just close it and I compile it. Okay, so next thing is I want to make this binary a process. So I have this memory, and this is an ELF file dynamically linked and it is not stripped. And for making it a process, what I need to do, I need to run it in background. So if I run this process in background, I'll get a process ID. If you see here, 3544, and I get the address of the local variable as well as the variable that is allocated in the heap memory. Okay, so I have a command of pmap to check the process state. Okay, small x. Okay, and we have a stack segment here. The starting address of the stack segment is shown here. Okay, and we have a heap segment as well, that is somewhere here. Okay, so we already print the address of the variables above, so we can check it out. Okay, so here we have this address. This is of a local variable. So if I copy it and try to check this address where it falls, so you clearly see here it is. So this part is same. Okay, and after this 92 something address is there for the local variable, so it's come into this segment only, stack segment. So what about the heap segment? So if we check the heap segment here for this memory, you will get something here, because this is the starting of the heap address. So we have double five c 365 and 08. See, it's after this. So this is the starting address of the heap. So all the memory is been located in here. Okay. So this way we can think of all the variables and the memories that is allocated in which segment of the program. Okay. So here we mentioned some of the detail of all the five segments. Okay. So here we have the text segment. It contains the executable instruction of the program. We have data segment, store initialize global or static variables. BSS also stores uninitialized global variables. Okay, and we have the heap segment that have the dynamic allocated memory, and we have a stack segment used for the function called local variables and the return addresses. So this way, this gives you the base of creating the memory layout of a C program. So thanks for watching this video. Let's see in the next video. Thanks.